In this video, I'll be going over the solution to expected change from February challenge. So first, I'm going to go over the explanation of the sample test case in the problem statement, because some people mentioned that they didn't understand the problem that clearly and they didn't have a sample explanation. And then I'll go over two different solutions, and I believe that these two solutions both have very interesting concepts to learn from, so that's why I'm going to present two solutions. Okay, so now I'll go over the explanation for the sample. So we have this string over here, and then it says first we need to uniformly randomly choose a pair of integers LR such that L is smaller than or equal to R. Now we need to consider the substring from L to R. So basically first we randomly choose a subarray of the string S, and then we do some process over this subarray, and then we want to know the expected number of characters that we will change. And by expected numbers, basically the problem means that we want to find the average number of characters that we would change over all possible cases. So basically over all possible substrings that we choose. And yeah, so basically for substrings of length 1, you have 5 of them. You have these for length 2, these for length 3, and these for length 4 and 5. Then all you want to do is find the answer for each of these 10 substrings, and we'll calculate the average of them. Then that average will be the expected value. So I'll go over how to calculate a specific substring. So start from the beginning of the substring, and then you start with the number of changes equal to 0. And then you also keep track of O, which is the number of opening characters, and C, which is the number of closing characters. So let's process the first character. Move here, and O increases by 1, and nothing happens. And then we process the next character, and C increases by 1, and nothing happens. Then we process the next character, and C increases by 1 into 2. And in the problem statement, it says that whenever the number of closing characters becomes greater than the number of opening characters, like it says here, then we must change this into a new character. So after we change it, what happens is number of changes increases by 1. And then also we need to change the counts of these. So number of opening becomes 2 and the number of closing becomes 1. Okay, so the answer for the subarray would be 1 because we have a total of 1 change. And let's look at another substring. So start at the very left, and O and C are both 0. Now we process the first character, and C increases by 1. And then O is greater than C, so that means we need to switch this character. Then you update the number of changes, the number of opening characters, and the number of closing characters. Then we process the next character, which is a closing character, and we increase C by 1. And since O is still greater than or equal to C, nothing happens, and we don't change this character. So the answer for this substring would also be 1. So after we calculate the answer for each of these substrings, as you can see here, what we do is we add them together. So the sum of all the answers here is 4. And then we divide it by the total number possible, the total number of cases in order to get an average. So in this case, we have 15 subarrays. So the answer would be 4 divided by 15. And then it says in this section here that this expected value can be expressed as a fraction p over q. And we find that p is 4 and q is 15. So what we need to do is we just calculate the inverse of q modulo this mod, and then we multiply p and the inverse of q together in order to find the answer. So we calculate this thing, and then after we do that, we should get the answer, which is shown here. Okay. So now I've finished, I've pretty much explained the sample, and now I'll start talking about the first solution, which uses a combination of dynamic programming and contribution technique, or you can call it linearity of expectation. So in order to calculate the average, first we need the sum of the number of changes over all possible subarrays. And then instead of calculating this, what we'll do is for each index I, we'll calculate the contribution of I to the answer. So the contribution of I to the answer turns out to be the number of subarrays which change index I. So for each I, we'll calculate this. And then after we calculate the contribution for each I, we can add it up in order to find the sum of the number of changes over all subarrays, and then we'll divide by the number of subarrays to get our average. And I'll find a few contribution technique problems and I'll include them in the description, just in case if you aren't familiar with the contribution technique. So what I mean by that is, for each index in the string, we'll calculate its contribution, which is the number of subarrays that will change this index. So obviously for the opening parentheses, these won't ever be changed at all. So the answer for the contribution for these indexes are 0. And then what about this index over here? Well, we can find out that for this index, in this subarray and in this subarray, we'll change this index, we'll change the value of this index. So the answer for this index is 2. Then what about this index? We find that in this subarray and in this subarray, we'll change this index. So the answer for this index is 2. And then basically we just add up the contribution for each index, which is 4. And then we'll divide by the number of subarrays, which is 15, and that basically gives us the same answer. Okay, so yeah, as I said earlier, we just sum up the contribution over all I. And then this is where the DP comes in. So let's define this dynamic programming matrix. So dp of ij will be the number of starting subarray positions L, such that when we process the subarray from L to I, we have the number of opening characters minus the number of closing characters will be equal to exactly j. And the reason why we want this as a state is because whenever O minus C becomes negative, that means that the number of closing characters is greater than the number of opening characters. And that's when we need to change the closing parentheses into an opening parentheses. So I'll give an example of what this DP of this DP. So if we have this string over here, and these subarrays are the subarrays which end at index 3. So for this subarray, after we process it from left to right, we'll basically change this into and opening parentheses, and the subarray will look like this. And then for this subarray, we also change the first parentheses into an opening one, and for the last subarray, we don't change anything to it. And if we calculate the number of opening minus the number of closing characters for each of these subarrays, find that the first subarray has a sum of 1, the second subarray has a sum of 2, and the last one is equal to 1. So in this case, since we end the subarray at index 3, we have dp of 3 of 1 is equal to 2, since two subarrays have an O minus C value of 1. And then we have dp of 3 of 2 is equal to 1, since one subarray, which is this one, has a value O minus C of 2. Okay, so now we need to figure out how to calculate the transitions for this dp. So first, we need to add 1 to dp of I minus 1, 0. And this represents the empty subarray starting at index I. And we need to add that before we process character I. And before we process character I, the subarray is empty, so sum here is just 0. And then next, we have to do some casework. So if the new character is an opening parentheses, then our value O minus C will increase by 1. So what we do is we set dpi of j plus 1 equal to dp of I minus 1j. So all j increase by 1. If the new character is an asterisk, then the sum doesn't change at all. So the dp array, the new row of dp will be the same as the old row. And if the new character is a closing parentheses, then the sum will decrease by 1. So we go from j to j minus 1. However, when we add a closing parentheses, some of these sums, they might become negative. And remember, when the sum becomes negative, we need to change the last closing parentheses to an opening parentheses. So we know that the negative sums have sums of -1. So using this dp, you can find the number of sums which are negative. And while we know the value of this dp, we can use this value of dp to calculate the contribution for index I. So the number of subarrays which change I is equal to the number of possible starting positions of the subarray multiplied by the number of possible ending positions. And if you remember our definition of the dp, our dp means gives the value of the number of starting subarray positions. So we replace this with the dp value. And as for the number of ends, basically any end which is greater than or equal to I will be the possible end for the subarray. So we multiply by n plus 1 minus I. So after we use this formula to calculate the number of subarrays which change I, that's basically the contribution for I, so we add that to the answer. Okay, and notice that for negative sums, when we change the closing parentheses to an opening parentheses, the sum increases by 2. So before, so this one value of C becomes an O. So that's why the sum increases by 2. So we have to update that in our dp array as well. So what we do is we add the number of sums, the number of starting positions which cause a sum of -1. We change it into a sum of 1, and then we set the negative ones, the dp of -1 to 0. Okay, so for this dp, we have O of n squared states, and each state requires a constant time transition, so the total time complexity of this dp is O of n squared. This doesn't pass all subtasks, but this is okay, because many solutions are found by optimizing slower ones. So what we can do, so the main bottleneck of this dp is doing the shifting of the dp between row transitions. So shifting is linear time. So for example, if this is row I-1, and then if we have an opening parentheses, then all the sums increase by 1. So the new dp looks like this. And we'll try to optimize this. So we'll create another array D, and then this array D will store the dp values. And instead, dp of I-1, 0, it will be a pointer to the array D. So 0 will point to this one. So whenever we want to access dp of I-1 of 0, we just look at the pointer and then we know which element to look for in D. And what if we want dp of I-1 of 1? Then we look at the pointer and we add 1 to it. And the same thing happens for other values. So if we want dp of I-1 of j, then we look at the pointer for dp of I-1, and then we add j to the index in order to find the value in D. Okay. So what if now we want to shift? So when we shift, what we can do is we can look at the pointer for the previous dp row. And then, for example, if we want to shift the array right, then we'll just move the pointer left. So in fact, dp of I of 0 will point to this new element over here. And you can see that this works. So if we want dp of I of 1, then we just look at the pointer which points to D, and then we move 1 to the right, which gives us 1, which is the element that we want. So notice that moving these pointers, you can implement it in constant time. So how I actually implemented it is, while I run the dp, I keep track of an offset, which I call O. So if I want to access the value of dp of I of j, instead I access the value d of O plus j. And then when I want to shift the sums up by 1, I'll subtract 1 from the value of the offset, so that when I query j plus 1, I get j from the previous array. And then when I want to subtract the sum by 1, I add 1 to the offset, so that when I query j minus 1, I get j from the previous array. Yeah, so this is pretty much it for the explanation, and I'll show you the code, which is really simple. So first we input n and s, which are the strings, and then we reset the array D. And note that we start with an offset of n. The offset that you start with doesn't really matter, but you want to choose a big enough value, because if the offset becomes negative, then you will end up querying negative values, the negative indexes in the array D, which is bad. So in this case, I set the offset to n, and I set the size of the array D to be 2 times n plus 1. So now I just implement the transitions for the dp. So remember, at first we add 1 to dp of I of 0, and this is shown over here. So because of the offset, dp of I of 0 becomes d of O. So I add 1 to d of O, and then I just process over the cases. So first, if the new character is an asterisk, then nothing happens. So I don't do anything when the character is an asterisk. Then next, if the new character is an opening parentheses, then that means we add all sums by 1. So we shift everything by 1, which means that we subtract the offset by 1. And then the last case is when the new character is a closing parentheses. So if that's the case, we subtract 1 from each of the sums. So we shift the sums by -1, and instead we add 1 to the offset. And after we shift the array, we need to process the negative sums that we might have. So first we need to calculate the contribution of I, and then we need to add 2 to the negative sums. So for this part, basically I use this formula over here. So I take dp of I of -1, which in my code over here is just d of O minus 1. And then I multiply this by the number of n's. So in my code over here, I use 0 indexing, so the formula looks a bit different, but actually they're doing the same thing. So after I calculate the contribution of I and add it to the answer, I increase the negative sums by 2. So for each sum which is equal to -1, I add the number of sums which are -1 and change them into sums which are 1. And then I remove the sums which are -1. And then the last part of the solution is our sum is stored in answer. And then in order to find the expected value, we need to divide by the number of subarrays, which is n times n plus 1 divided by 2. So I multiply the answer by the multiplicative inverse of the number of subarrays modulo m. And then I output the answer. So this is pretty much the first solution. Okay. So the second solution also uses a DP, but it uses a stack as well. So let's define the DP. So DP of I will be the total answer for all subarrays which start at index I. And this definition is pretty straightforward. So let's see how we can transition. So the first case is when the character I is an opening parentheses. So in that case, let's find J. And J is the first index such that when we start from I, we will get the number of opening characters will be smaller than the number of closing characters. And we can find this closing parentheses with a stack. And I'll show it in my code later. So after we find J, so notice that none of these characters are changed because in this part, O will always be greater than or equal to C. So this is the part where it starts to change. So in that case, basically you can just set dp of I to equal to dp of j, since the number of opening parentheses and the number of closing parentheses are the same within this prefix. So these starting from I and starting from j are basically the same thing. Okay, so now we have the next case when I is a closing parentheses. And obviously, for any subarray which starts at I, we're going to need to change it. So there are a total of n minus I subarrays which start at I. So for each of those subarrays, we need to increase the answer by 1 because we add 1 to, because of this index which always changes in all of the subarrays. And then let's pretend that we change, while we process this, we change this into an opening parentheses. Then we can do the same thing that we did for the other case. You can also use the stack to find the first occurrence, such that the first j such that the number of opening characters is smaller than the number of closing characters. So our final dp transition for this case is dp of I is equal to dp of j plus n minus 1. Okay, so for the code, basically I have my input here, and dp of n is just defined to be 0, and then we process over the cases. So in our stack, we basically store the closing parentheses which aren't matched yet. So if our new character is an opening parentheses, and that means we try to delete a matching closing parentheses. So if the stack is not empty, then we pop something off the stack, and then we find the first closing parentheses which cannot be matched. So basically j here, and if the stack is empty, then it's just the n, and otherwise it's the top of the stack. So otherwise we'll basically have stored all of the closing parentheses which aren't matched yet in the stack. So if we look at the top of the stack, then we will find the first one which is not matched. Then we set dpi equal to dp of j. Okay, so that's the first case. The second case is when the new character is a closing parentheses. So in that case, we know that all subarrays starting at I will change index I, so we start out with an answer of n minus I. And then basically we pretend that we're going to change this closing character into an opening character. And then we try to match the new opening character with another closing character. And we basically pop it, and then we basically use the same process to find the first closing parentheses which can't be matched. So and it's pretty much the same as the one for the other case. And we add dp of j to dp of I. And then we need to revert the change, because the change of I from a closing parentheses to an opening parentheses was only temporary. So we need to put the closing parentheses back into the stack. And then finally, we need to add the current closing parentheses into the stack. And then the other case I didn't mention is if the new character is an asterisk. So if it's an asterisk, then nothing happens, so you can just set dp of I equal to dp of I plus 1. And then finally we add up all dp of I in order to find the total answer, and we use the same process to find the final expected value. We just multiply the answer by the multiplicative inverse of n times n plus 1 divided by 2. And then that's it. So if you have any questions or any comments, just feel free to leave them in the comments of this video, and I'll check them, and I'll try to improve the more you comment, the more I can improve my explanations. So yeah, feel free to do so.